In describing waves, some parameters or properties are normally specified. One of these properties is amplitude A. The amplitude of a wave refers to the maximum displacement of the particles of the medium from their original position as the waves propagate. If we take the time it takes for each particle of the medium to move from its original position and back, we actually determine the wave period t. The period of waves refers to the time it takes for each particle of the medium to complete one cycle of motion as waves propagate. If we take the reciprocal of the period, we will get the frequency f of the waves, the number of waves produced by a source in a unit time, for example, 1 second. Frequency may also refer to the number of complete cycles of motion of each particle of the medium in a unit time. As waves propagate through a medium, we can see that certain parts of the medium have the same displacements at a particular instant of time. When we measure the distance between these parts, let's say between points of maximum compressions, we will get the wavelength lambda. Waves propagate through a medium at a certain speed v. When speed is multiplied with period, we will get the distance covered by the wave in a unit time, which is also the wavelength lambda. As frequency f is equal to the reciprocal of period t, transferring f to the other side of the equation gives us the familiar formula v equals f lambda. This formula can be used to calculate wave speed v when f and lambda are known. It also shows the inverse relation between f and lambda, which means that for a particular medium with fixed properties, as frequency decreases, wavelength increases while the speed remains constant. Many students believe that increasing frequency of wavelength will result in the increase of wave speed. Do you agree with them? When you listen to an orchestra, sounds coming from different instruments are produced at the same time. These sounds are of different pitch and loudness, but these sounds reach your ear at the same time and blend harmoniously. This occurrence means that the sounds produced by the instruments propagate at the same speed despite the difference in their frequencies and amplitudes. For media such as air, spring or string, wave speed changes only when the properties of the medium change. Look at the snapshots of the motion of two wave pulses on identical springs created at the same time but with different shapes. What do you observe? The waves are at similar positions at the same points in time, which indicates that the waves move at the same speed. Now look at the snapshots of the motion of two waves created in the same way at the same time but using springs under different tensions. The lower spring is under less tension than the other spring. What do you observe? When a spring is under less tension, its particles experience weaker interaction forces. The spring will have lower tendency to restore its original form or shape, and the waves will propagate through it at lower speed. When the properties of the medium are unchanged, wave speed remains unchanged. This happens even if wave properties such as frequency and amplitude change. But what happens to the greater effort or extra energy used by an external agent in creating waves if the wave speed does not increase at all? The greater effort causes the particles of the medium to vibrate more quickly, or cause the particles of the medium to move farther away from their undisturbed positions. Greater energy will also be received by objects at the locations reached by the waves.